This is surfing West Virginia or somewhere. Who knows where it is. The rivers look too big for that. And so the relevance, I guess, for us is that we talked about the idea that if you're on a wave or if you're jumping a waterfall, I guess we can use Bernoulli to say something about the velocity of the water as it travels down a stream and then drops. It's actually F equals ma, so it's exactly the same as if I drop this pencil. The boat will go down in the air, obviously at that speed, like falling due to gravity. If you look at the drops of water as they go down at exactly the same rate. So perhaps not surprising. So everything that we talk about in this class is the underlying concept is F equals ma. If the fluid isn't moving, then there's no acceleration, so it's just F equals 0. And I suppose next week we'll start talking about resolving forces on structures due to fluids, and that's exactly the approach we'll use. Actually, we'll do a little bit today. We've already talked about, for instance, calculating pressures on systems. So that's the first eye candy to get going. So I'll make sure I turn it off so it doesn't keep on making sound. What else we got? Oh yeah, a bit more vocational. What's the split of people in this class? So there are 4 majors in our department. So we've got environmental systems engineers, we've got petroleum engineers, we've got mining engineers, excellent, and we've got energy engineers. Yeah, fine. So environmental systems engineers or petroleum engineers and mining engineers for that matter, drilling, and actually energy, if you're looking at geothermal energy. Drilling is a big deal. Why is it doing that? I don't know. I'm going to turn that off. Perhaps it doesn't. It's making that noise because I don't have the sound on. So drilling.
Here's an example of what can happen when cuttings are not removed off bottom.
So I'll give the narration. So drilling is a big deal. So the whole of Pennsylvania's economy is built off Marcellus survived their recession very nicely because of the extra money put into the economy by natural gas in gas shales. And so to access it, you drill holes down to 10,000 feet, 3 kilometers, scoot them across laterally, massively hydrofracture them to increase the permeability so more fluid will flow out of them, relevant to this class. But in the drilling, relevant to what we're talking about now, you'll typically use mud. Mud will keep the hole open by applying a pressure against it. It's usually not just water, it's usually mud, which is a mixture of water and bentonite clays in a suspension. And so that's denser than water, and so it pushes back on the well bore to keep it open as you drill down. And it's circulated down the center of the drill string, lubricates and cools the bit, and then comes up on the outside of the drill string in the annulus between the whole wall and the drill string itself. And so it carries up the debris that it drills up. It doesn't wear it away, but it breaks it up by these bits that sit on the base. And the other facility it provides, shown here, is that it provides a cake on the well bore, this brown film, to be able to stop the water, the drilling mud going into the formation, and therefore be able to exert a bigger pressure to keep the well open so you can get down to 10,000 feet or 3 kilometers without it collapsing on you and jamming the drill bit in place. And so that is something of relevance to the pressures at the base of the hole are exactly how we're calculating in this class. If you're an energy engineer and you want to drill holes for different reasons, home ground sourced heat pumps are a big thing these days. You drill a hole, not so deep perhaps, just to get below the frost line, maybe 2 meters, 6 feet down, where the temperature doesn't change very much. If you go into the ground here, anything below 6 feet to 1,000 feet, the temperature is something like 55 Fahrenheit, 10 degrees centigrade. And so you can use that low quality heat source, 10 degrees centigrade, to be able to circulate water to pull out that temperature up to a ground sourced heat pump, use it to provide the low quality heat in the heat exchanger, take the cool out of that when it's 30 degrees outside. So you use that 10 degrees centigrade heat with a refrigerator, basically, phase change, or air conditioner, to be able to suck the cold out of that to be able to cool your house. Likewise, in the winter, when it's 0 degrees centigrade outside or maybe minus 10 at night, you use that constant 10 degrees ground temperature to be able to pull out that warmth in the wintertime to be able to keep you comfortable in your house. And so I don't know whether they showed it. So they drill a hole, maybe it goes down 200 feet. They'll typically be just vertical. It could be just, you could excavate it, lay the pipe. So what you see here is pipe. It's two pieces of pipe, a down and an up, that will be grouted into the hole with concrete, cement. And so that will act as a heat exchanger, pumping warm water, say 20 degrees centigrade water down. It'll pick up enough cool as it circulates into the subsurface to bring that, cool down that water that's 20 degrees going in, comes out at 10 degrees, and then you use it in your house to be able to be super efficient in terms of heating and cooling. And of course, heat pumps were the way, after the Ukrainian invasion, how Europe, Germany, which was dependent really on gas from Siberia and the Nord Stream debacles, how they adapted to be able to deal with the lack of that supply, which they'd kind of relied on up to that time. So that's that. And finally, this is quite good as well. So watch this. So that's relevant. So again, you need to use the same ideas there to be able to drill a hole. So you're drilling muds to drill a hole and to lubricate the bit. And the other, in terms of personal responsibility, Malpasset is a dam in the south of France near Nice. I can narrate this one. Around the late 1950s, built for water supply, very dry in the south of France. Apparently has Roman aqueducts in it, as you'll see, which used to supply water from the mountains. The Alps are just behind it. And it was built around the late 1950s, a very narrow arch dam, as you'll see, Roman aqueduct, and it failed. Failed on its first filling. You can read as well as I can. And when it failed, it killed 400 or so people as it breached the dam, and all the impounded water, which is typically a very large amount, you want it to be there for water supply, flowed downstream. And of course, people primarily like to live by rivers in the bases of valleys rather than the top of mountains. And as a result of that, you're in this constricted space, and all of a sudden, if there's a load of water that's coming down uncontrolled down your valley, then if you're close to it, then you probably can't get out in time if it's an unannounced failure. If it's something that's raining and it's topping, getting higher and higher, and you're worried about it being overtopped, and then the flow starting from there, at least you have some kind of warning. But this was, it was being filled by rain, but perhaps they weren't so worried by it. And so they tried to clear it. As a result, they didn't. I guess you'll see in a moment the result of the dam being breached. I think the dam is still largely there, but obviously it's breached. It moved because the abutments that provide the arch dam, right? So the arch dam is arched upstream, so you're pushing against the arch, just like you'd have a stadium roof is arched that way. Structurally, it's quite sound. So it relies on the abutments that it pushes against. They actually moved, and the dam cracked, and as a result, the water went downstream, and so on, with not very good results at that time. And there was another disaster in the Alps shortly after that, the Vion disaster, that was also an arch dam that failed. And so, public good, engineers, you design for what you know at the time. Perhaps things weren't known so well. The failure wasn't in the dam concrete itself, which was plenty strong enough to be able to resist what was going on. The problem was the abutments shifted because there were faults, joints and fractures in the abutments. It moved. The dam is quite brittle. When it moves, it fractures, and as a result, the water flooded downstream. And so when we move from this class, now we're talking about fluids at a point. First week was fluid properties. Second week, this week, is how the pressure at a point varies from the weight of fluid above you in the swimming pool and the weight of atmosphere above you up to the troposphere. That's why we get a pressure at that point. We need to take account of all of that material above us. If we work in great gauge pressures, zero pressure now, we don't need to worry about the atmosphere, but we worry about the water above us when we're down at the bottom of the swimming pool. And so you can imagine that on the wall of the swimming pool, as a result of that pressure, there's a small pressure at the top, and it gets progressively larger and larger as you get to the base. So if you have an above ground pool, you have to design to be able to take care of those forces. And so the next thing we'll talk about next week is forces on structures, which follows naturally from what we've talked about now. We'll talk about fluid statics until we get to week 4. Week 4, we'll be talking about Bernoulli's equation. So we're talking ostensibly about the kinds of analyses here, dam break analysis, how waters flow and how they move. And they move according to Newton's second law, which you can convert into Bernoulli if you've heard of Bernoulli before. And you don't need to have done, because we'll deal with that next time. Okay? So that's the starter, the eye candy to get going today. And I don't know. Oh yeah, we should look at this. Just because I think it's funny. Who would do this? Well, yeah, I think it's real. But the other interesting thing about this, you can look up, look up Google lawn chair balloons LA airport or something. So some guy did this. So he said to his wife, I think I'm going to go for a ride. I've got a lawn chair. I'm going to attach some balloons to it, and I'm going to take a BB gun with me, because when I get too high, I can shoot the balloons out and I'll go back down. And he did this. And so this guy apparently was spotted by planes landing at LAX at 16,000 feet or something. Not this guy, but some other guy. So anyway, so actually I did, maybe I put that on there. So this guy, that's kind of crazy. Isn't that crazy ass? I think it's crazy ass. Maybe I added it. Yeah, I guess I did. All right, so I did last night. So at 11 o'clock I added it. So I won't go through all of this, but you get the gist. Larry Waters, lawn chair, LAX. Oh, yes. Perhaps we should spend some time. Fine. Yeah, so you get the idea. I don't know the rest of this. They have some stuff. Actually, this is a sense. I think this is a recreation, but this is the idea. Perhaps it's not a recreation. But that looks like a lawn chair. That looks like some ballast. That looks like a load of balloons. I don't see any airplanes landing at 16,000 feet, but I guess it goes through what you see. Yeah. Yeah, I know. Seems to have captivated you. I think it's kind of funny too. So. Yeah, it's quite a nice graphic, isn't it? So you went up to 16,000 feet. Well, well, LA is essentially at sea level, so 7,000 feet is a long way up. Cessnas. Pipers used to be built in Lock Haven, Williamsport, close to here, in case you didn't know. Yeah, so fine. You get the gist, so fine. All right, now I've got your attention. Let's do some real stuff. So, okay. Yeah, funny stuff. Where's notability? All right. Maybe ease into it. Well, we talked about pressures last time. The one thing we didn't talk about is how we talked about how you measure pressure. Barometer obviously is one way to do that. Measures very subtle changes in atmospheric pressure. So the lowest lows in the most violent of hurricanes are something like, it goes down, a bar is 1,000 millibars, which is normal atmospheric pressure. The lowest low in the most intense hurricane is something like 900 millibars. So 100.1 of an atmosphere below normal. And so we want to measure those pressures with the barometer because it says something about how weather is changing or would be. The other ways that we can measure pressures are using what's called a Bourdon gauge. Must be named after its inventor. It's just a closed tube that's has a pressure in it, that has a bend in it. When you change the pressure in it, it tries to straighten itself up, and as it straightens itself up, you could tie that and measure the displacement of the tip of it to be able to calibrate that against the change in pressure. If you want to measure pressures in the ground, one way which you can do it is you can use a piezometer. You can put a pressure transducer at the bottom of your well. You could also do it with a piezometer that looks like this. If you have a spring membrane here, you put a pressure, influent pressure on the one side. When that pressure equals the water pressure pushing against it, it will deflect this membrane and allow you to get a connection. And so the pressure you measure in the connection is equivalent to the pressure that's pushing due to the water. And the way that a pressure transducer works is kind of similar to that. It has a diaphragm that's sensitive to the pressure that's acting on it. It will displace as the pressure increases. And if you measure the displacement of that diaphragm, again, you can calibrate that to the pressure within the system. Tire gauges, it blows something up past the little stalk. And so it's a balance between the pressure acting at the bottom of that stalk and the pressure moving and the fluid moving around it that gives the height rise in the pressure gauge if you've used a mechanical pressure gauge. And of course, PZTs these days, piezoelectric transducers, merely take a crystal piece of silicon, you squeeze that silicon, you get a little electric voltage out of it as you squeeze it. If you measure that voltage, that gives you the pressure that's applied on it. So that's what most of them are these days. So the top is kind of old school dial gauges that work on the idea that if you put a little serrated ratchet on this and you have on the back of your dial gauge a cog, when that ratchet moves up and down, it'll turn the cog around and turn the arm of the gauge around to be able to say that. I guess you must have seen analog gauges in your life, I think, right? All right, let's get down to nitty-gritty of what we want to talk about. Today, all I want to talk about is close off with some examples of what we've already talked about in terms of fluid pressures at a point and manometry, working our way through systems. I'll just briefly talk about what we've already said. We said last time that the pressures at a point act uniformly in all directions in a static fluid. If the fluid is static, then accelerations are zero, and the big complicated differential equations we get resolve to two expressions. One is that the pressures as you move horizontally don't change so long as you can get to that place in a connected path. And always as you go up or down, the pressure changes according to the unit weight, and the unit weight is just the product of the density of the fluid times gravity. It's negative because our coordinate system, z is positive upwards, and so as you go down, pressures increase. It just takes care of that reality. If you integrate this expression for an incompressible fluid, a liquid, which is what we'll use, you can define pressure at a point as the change in pressure as you go down plus the original pressure from the point you started at. We'll look at that in a second. Well, actually, we'll look at that now. You can do it also for a gas. It gets a bit more complicated, and we won't do that. And the reason that if we look at this, how do I define this? This is, remember that this is, z is positive upwards, this is pressure, this is unit weight. This is only saying that if you start off at some point at pressure P0, if you go down some height h, then the new pressure is P, or P1, right? And that's all we've said. We make a distinction here in that this is H, not Z, because H is positive in this direction, plus VE. Sorry if I didn't mention that. This is negative Z in this direction, and that defines our manometer rules. And of course, the manometer rules make sense if we go through them. So you need to make this distinction that H is a height that we're measuring as we're going down. And it matters in which way we go. So if we go up, we subtract pressures. So I suppose if we started here And we went, let me do this. I'd be very fancy. Come on. My computer crashed yesterday, so I'm surprised. So if we go up, H, we subtract off pressures, subtract off height, and so we subtract off pressures. Right? That's what this one is. If we start off here and we go down, let me be fancy, because this is the essence of what we're doing. If we start off here and we go down, this H, and we go here, then this is the additive pressure, right? We go down in H, so we add pressure. That's all we're doing. This gradient of this line, if I extend it, is equal to, if we write out the change in pressure with depth, is equal to minus unit weight over 1, this expression here. Then we could do similar triangles and see what this is. This is dz, this is dp, and therefore if you do a similar triangle here, the gradient of this line is equal to unit weight and 1. It's just this expression. That's all it is. That's what the differential is. It says that you go down a certain elevation, z, the pressure changes by a certain amount. As you go down double that amount, you double the change in pressure because it's linear, at least in a liquid. And I suppose if we want to be rigorous about this, we know that if this is sea level, if this is z equals 0, then we know that above that we could think about having the atmosphere. And the atmosphere, there's a very small change in pressure for a big change in elevation because the density of water is 1 kilogram per cubic meter as opposed to 1,000. So a factor of 1,000 difference. And so that is why if we go horizontally, so if we go horizontally in a porous medium, in a swimming pool, then the pressure distribution horizontally would be exactly the same as this. I'm going to run out of space. Oh, didn't mean to do that. So, which means that if I go horizontally in two fluids, then the fluid pressure here and the fluid pressure here are exactly the same, right? They're below the surface of the water. So that is what this expression is. So if you want a physical meaning for all of these things, if it's evacuated, then the vapor pressure is the pressure it's at from the barometer, right? Was our example of doing that. So that's what that is. And if we're in a gas, then because the unit weight of gas or the density of gas is 1,000 times less than water, then there's almost no pressure change as we go up. It's very small. And so sometimes we can ignore it. Certainly in manometer systems, as we kind of saw yesterday, right? So that's kind of a summary of where we are. As I say, I was just going to go through some examples today, talk about suction. I'm not going to talk about micromanometry. We'll talk about mercury manometry. We'll talk about concrete forms, and I don't care about this slightly compressible fluids. Water, of course, is kind of incompressible, but nothing is absolutely incompressible. So if you go down 10 kilometers into the Marianas Trench, 10,000 meters, might be something like that, then the pressure that you get from assuming it's compressible or not incompressible are maybe off by the example in here by 1 or 2%. So not big enough for us to worry about. Okay? Questions? Stunned by my brilliance, right? Or perhaps just sleepy. Yeah. So. All right, so here's an example. Use manometry again. The question could be if we put a bucket, invert a bucket in the water, couple it up to a tube, lift that bucket up with the tube with a blockage in it so that it can apply a partial vacuum. What is the height rise that we'll measure in this manometer? How do we do that? So what we can do is we can use our manometer equations again. You can help me again here. We can start off with Start off from the place where you think you know something and work to the place where you don't. PB, we need to get to this point here. So what's the pressure at this point here? It's PB plus H minus 3 feet. PB plus the unit weight of the gauge fluid times H minus 3 feet. Sorry, we're working in British units. Hate that. We're in air in this, so if we go up here, the pressure doesn't change very much. So we can scoot right over here, and that's the same pressure as PA. So by the time we get here. And if we go from PA and we go down, then the pressure will increase by 2 feet times the unit weight of water. And that equals PB2 and so what do we know about that? PB is connected at atmospheric pressure to this point here. They're at the same physical elevation. So we know that PB must be 0 gauge or 100 kPa absolute. They're the same, right? 100 kilonewtons per meter squared. PB1 must be the same. Much easier to work with 0 rather than 100, so let's do it in gauge. 0 pressure we feel now. And so if you rearrange this, what do we want to do? I guess we have gamma gauge times H is equal to, if we separate these off and to the right-hand side, so this would be, I think, plus 3 feet times unit weight of the gauge fluid minus 2 feet times the unit weight of water. I think that's right. And if we divide both sides through by gauge fluid, this becomes 1. This becomes gamma gauge. This becomes 1. And this becomes the ratio of the gauge fluid to the water. So whatever the gauge fluid is, it's 2.5 times the gravity of water, so gamma gauge equals 2.5 times unit weight of water, 2,500 kilograms per cubic meter, or roughly 25. So this is roughly gamma gauge equals 9.81 meters per second squared times 2,500 kilograms per meter cubed. I know I'm writing small. And that's something like of the order of 25 kilonewtons per meter cubed. Just like water is roughly 10 kilonewtons per meter cubed, 9.81 kilonewtons per meter cubed, right? You have to get used to doing this. Of course, these are in feet, so I've screwed up, but it doesn't matter. You get the idea. And so if you work it through, then you find out that the gauge height is actually 2.2 feet. That means that actually the level would be here. So it comes out with the right value. It tells you exactly what it is, and that's what you'd expect. We said before that if the pressure is high inside the container, then the manometer is probably going to be down and up on its final limb. So if it's the opposite, if there's a vacuum in the container, you think that it's switched, and so this level you'd expect to be high and this level to be low. If you wanted to, you could calculate the force to apply upwards. R would be equal to the area of the tank, which would be this, not a length, but an area of the tank, times PB, and times PA, which you'd calculate, but it would also be equal to 2 feet times the unit weight of water times AT. You could do it two ways. You could calculate what the pressure is here by writing your manometry equation to get to this point, and then multiplying that pressure by the area. It has to be pulling down on it if it's a weightless system, because you can draw a free body around this that would isolate this section here. And it would isolate this section with a force pulling upwards and a pressure distribution, a vacuum pulling downwards, PA. So you could do that. Or you could do what we did with the capillary tube. We could realize that this pressure is atmospheric here. We can cut this system off here, so it's atmospheric underneath it. And then we're just pulling up a cylinder of fluid. And the cylinder of fluid is 2 feet tall. This is 2 feet tall. And it has an area, AT, and it has a force acting on it, which is R. Right. So often you can solve these problems in different ways. Yeah?
How did we know that the gamma gauge came first and then the other gamma came after?
In this here,
In
in this initial question. So you start off here. It's atmospheric. You want to get to this point here. We have to go down through the gauge fluid. And so the pressure change that you're experiencing is in the gauge fluid. And so it has to be H down through the gauge fluid and 3 feet back through the gauge fluid. And so this is the journey that you've taken through here. So it's whatever fluid you're traveling through to get to the point you want to get to.
So how are the two gammas different?
They're different properties. This is mercury here. Well, it's not mercury because it's something that's 2,500 kilograms per cubic meter. If it's mercury, it'd be 13,000, right? So I don't know what this gauge fluid is. There might not be any fluid that's 2,500. But this is water. So, yeah. So it's a bucket that's placed in water. The gauge fluid is a different fluid. The gauge fluid could be also water, but the height would be much higher. It would be a couple of stories, yeah.
How did you develop the relationship between gamma G and gamma W?
Standard result. The definition of specific gravity is what you multiply the density of water by to get the density. So the density of a fluid is equal to specific gravity times density of water. This is always 1,000 kilograms. Standard result. So the specific gravity of mercury would be 13.6, right? Yeah. So, more than one way to skin a cat, as they say. I don't know where that expression comes from. It seems crazy ass to me. So, anyway, that's what they say. Bob's your uncle. Another one? Okay. Let me explain the thing in detail. These bulbs are pipes going into the page. This pipe has fuel oil in it that fills up the whole cavity down to here. And then there is mercury, which is located here. This pipe has SAE. SAE must be Society of Automotive Engineers oil in it, which has a different density. Let's not worry about what those are. And it also has an air bubble in it. Air bubble, kind of interesting, right? What happens if you take a piece of hose pipe? If you want to be able to put a foundation in and you want to move a level from left to 20 feet over here, you can do that quite well with a piece of Tygon tubing, because the water level in the tubing here and the water level in the tubing here will be at the same horizontal level. So think about taking a tube with an air gap at the top, put your thumb over the top, turn the tube upside down with your thumbs over it. What's going to happen to that air pocket at the bottom? If the tube's large enough, it's going to travel up to the top of the tube, they'll join each other, and they'll sit as an air bubble. That's exactly what you have here. So the pressure, the level at this point here, if it's an air bubble in that tube, has to be the same on both sides, right? So that has to be at the same level. So that's the trick for this one. Tricky trick, but it's trick nonetheless. So what are you asked to do? A mercury manometer, fuel, determine the pressure in pipe B. And so if we want to figure out what PB is, let's start here. So PA, do we know it? I think so. I don't see it, but it must we know it. Oh, we know this. I'm not going to work in. So I'm not going to do the units here. I'll embarrass myself. But we have this pressure here. Okay, we're going to go from here down to this point here. So we'll have to go 3 inches plus 18 inches. So we're going down. 3 plus 18, you divide by 12 because they're in feet, because they're inches to feet conversion. And that gives you the pressure here. And it's going to be the unit weight of fluid A. So now we're here. Now we want to get here. We're going to go down and back up. So we could go 6 plus 7 down and 7 up, or we can just go 6 down. So we're going down again. So we add 6 inches over 12 times the unit weight of mercury. And that gets us to this point. We're going to go up. So we subtract to get to this point 18 plus 6. Over 12 times the unit weight of fluid B, right? This is different fluid. So now at this point, that's where we are. We're at the same level here, so we can go across, because dP dx equals dP dy equals 0, just for the argument with the bubble in the upturned pipe, and we end up here. And if we want to go down to this point here, it's 3 inches up to here, and it's 5 inches down. So we're going down, so we'll add 2 inches, which is 3 inches up times unit weight of B, and that equals pressure B. And I think you have, it's exactly the same expression here. So it's just that we've done it interactively. And so I'm not going to substitute the values, but if we know the unit weight in tube A, we know the manometer fluid, we know the density of the fluid in B as a specific, is it specific gravity? Yeah, specific, we have a specific weight. And for the different ones, and we know that pressure A is this, and so we get this. And it turns out to be this. Okay? Yeah.
So the air bubble really doesn't contribute to the pressure at all?
No, it has to be for I think the best analog is that Tygon tube turned upside down. Was it you asked the question of how thick the manometer tube should be last time? Yeah. So you want the manometer tube to be thin enough that a bubble can't pass up it, but not so thin that you have capillary forces applied at the meniscus that affect it. And clearly in these tubes, if you turn it upside down, the bubble goes up to the top, it sits at the roof, and you can imagine the bubble has to have the same level on both tubes. If you shift one tube, it'll rearrange, the bubble will rearrange itself so it straddles an equal area at the top of the tube, if you can picture that. I think it's, so anyway. Yeah, we've got time for this. This is kind of a fun one as well. Again, there are 2 ways to skin a cat in this one, and it's set out for you to be used. So the idea here is you're pouring a concrete step. The top has to be open to get the concrete in, but because you're pouring liquid concrete in it, which has a mass to it, which will not only push against the side walls of this thing, it will also have an uplift. You have to be able to put a weight, a sandbag on it, to be able to keep it down. The top is open, and you want to know what the weight of the sandbag would have to be to keep it down. So what you can do is you can draw a free body diagram around this thing. So the way they do it in this example is to do it this way. So the free body diagram is around this whole thing. and it's just a statics problem. But the free body diagram has on its base acting a pressure, which is this pressure here. So you're lucky that I'm stupid, because that's why I can explain things well. You probably don't think I can explain things well, but sometimes if you have really brilliant professors, they are on a different level from you and they can't see how things get explained. So this is Z, right? This is the pressure change with Z. And so if you look at this depth here, so if you look at this depth here, this is your H. Then this is going to be PA, right? So we know that PA is equal to P0 plus H times unit weight of concrete. H you have, this is definitely 0 if you take it as gauge pressure. So you have that magnitude. You know what this is. You know the height is 8-inch risers and 10-inch tread. Riser is the step height. Tread is the length of your foot. And so we know the dimensions of this. And so you know that this is 8 plus 8 plus 8, which is 24 inches. So that's 2 feet multiplied by the unit weight. I hate British units, but you get the idea. And so you can draw a free body diagram from this. So the free body diagram is going to be the weight of the sand, WS, the weight of the form, the wooden form or metal form you have, and the weight of the concrete which is in filling that form. It goes in through the top, so there's no, this is open, it doesn't matter. And at the bottom, the pressure that's acting up will look like this. So there's going to be a force that's applied. Don't crap out on me. The infinite, oh, it did something. Okay, it did something here. It was thinking, it was frightened that I was going to do something to it. Give it a damn good thrashing. This is PB, sorry. So, fine. So this is an area. The area is going to be what? It's going to be 10 plus 10 plus 10. It's going to be 30 inches by 36 inches. I'm not going to mess with the units, but you get the idea. So you have an area. So if you know what the pressure is, because you're at a depth, then you know what this PB is. If you know what the bottom area of this is that the pressure is acting on, you have a force. So this gives you a force which we'll call uppercase P. Done as this. This is P. And so you can calculate what we want to know what this is. We can do force equals mass times acceleration, no acceleration. Forces in the y direction have to sum to 0. We don't care. They don't affect the force acting vertically. So we sum forces in the x direction, and so the sum of forces in the x direction also have to equal 0, no accelerations. That's what this is. Sandbag acting downwards, concrete acting downwards, form acting downwards, pressure acting upwards. And so if we do the calculations to figure out what the pressure is from this, what the area it acts on, which is going to be 36 inches by 30 inches, right? The base of this here. So we have this. The weight of the form we're given, 85 pounds. Specific weight of concrete is, I guess SG must be 2, right? Specific weight of water is 64, I can't remember, 64 pounds cubic feet. So this is a bit less, it's 1.9, I guess. So this is SG, about 1.9, I think.
Is there a particular reason why?
Yeah, shout, sorry.
The signs of the forces are flipped?
where?
for weights, and then the weights pushing down, and then
You can choose any direction, either direction, yeah. So long as you choose a direction. Yeah. It doesn't have to be Z upwards. But you're right, if we were using that sign convention, that'd be the opposite. Good question. So we know the weight of the concrete because we can calculate the volume of this, right? The weight of concrete is equal to the volume of the form, or the volume of concrete multiplied by the unit weight of concrete. You can do that. And we know the weight of the form. And so the only thing that we don't have is the weight of the sandbag, which is the object of our desire. Okay? And you can see how they do it there. You have these in your notes, so you can check it. So that's one way to do it. There's another way to do it. And so sometimes there's no single right way of doing it. I'm going to upset you all by removing this, but you get it in the video. Oops. Well, perhaps I'm not. I was going to delete it. Not doing a very good job here. My dexterity must be off. The other way we could do this, not of course, but is this. Let's draw a free body diagram that looks like this. And so if you're happy with the other explanation, ignore this. You could do it that way. So we could do a free body diagram that excluded the concrete mass. So this, obviously these two free body diagrams are joined, right? Because there's the whole side of this form, this here, the side of the form with steps going up joins the front side to the back side. And so what we could do instead is we could just look at the pressures. And the free body diagram for that would be to take the pressure that's acting here. This would be P1. And the pressure acting here, which would be P2. So that would be this length here. And that would be bigger, right? And we could call this area 2, and we could call this area 1. Area 2 and area 1 are going to be 8 inches by 36 inches, right? This would be 8 inches by 36 inches. Horrible units. Who invented those damn units? And so we could do a different free body diagram. The free body diagram would be P to A2, which is a force acting upwards, plus just keeping the same sign. Actually, this is in the right orientation, right? Positive upwards. This would be P1 A1 minus equals 0. So what we've done is we've made a free body diagram that we can calculate the forces acting on this. It completely excludes the volume of concrete in the form, but the effect of the concrete in the form is included in these pressures. We know that the pressure acting on this base, actually that's another important point, has to be uniform across this base. It can't be the height of the stuff above here, because we know as we go horizontally in a static fluid, the pressure has to be uniform. It has to be equal to the full height of this. It's not just the height of the fluid above it. And so if we calculate what the pressure is acting on this step, acting upwards, pressure on this step, acting upwards, and the weight of the sandbag, sorry, minus the weight of the form, right? That has to go in here as well, right? The weight of the form is included inside this red line. The weight of the concrete is not. Okay? So if you don't like that solution, don't worry about it. Go with the first one. But you should end up with the exact same answer. I'm not brave enough to try and see if I do get the same answer here, but you would get the same answer. Okay? So, no, I'm not doing this. No, this is just the example I talked about. We often assume that when we, that for a liquid, that the unit weight for a liquid equals constant. But as I say, if you go down 10,000 meters in the Marianas Trench, or to see the Titanic, as was done last year with the imploding submarine, then at those very extreme pressures, the compressibility of water is finite. And so if water is compressing, that means it's more dense at deeper depths, just like air is more dense at deeper depths in the atmosphere. It's 1 kilogram, 1.2 kilograms per cubic meter here. Top of Everest, it's almost nothing. And as a result of that, if it's more dense, then its weight is larger. And so if you assume it doesn't increase in density with depth, you wouldn't get the same pressures. And they go through this example, and they come out that if you account for compressibility, it ends up being 61 MPa more because you get more mass because it's compressible. And if you ignore compressibility, 60.6. So it's off by about 1 in 60, maybe 2%. And I'm not sure how deep it was. Does it say? Can you see it? Is this, okay, I didn't see it. I'll take your word for it. 6 kilometers. So, okay. All right. So that's that takes us through the first 2 classes. Don't pack up yet. We've got 5 minutes. I just want to talk about the test, which is not next week, but the week after that. So we've gone through the first 2 weeks. First is material properties, which is density, viscosity, interfacial tension, compressibility modulus, wave speeds. Things at a point, which are or material properties which define behavior at a point. This week we've gone through to look at pressures at a point. We realize that to get pressures at a point, it matters that everything around us and above us contributes to that. The pressure we feel here, 101, I call it 100 kilopascals absolute, is because the weight of water, weight of air, and gravity acting above us, which pushes down here. And that acts on the water in our swimming pools in an additive fashion. So the pressure at a point relies on everything above us. And it's really vertically so far that we've worried about things. So from now, we'll start talking about pressures on structures. Malpasset Dam is a case in point, and that's next week. In week 4 and 5, we'll start talking about moving fluids. So when the Malpasset Dam collapses, then it flows downstream. How quickly does it flow? How do we calculate that, etc. And then we'll move on from that. But we've finished the first 2 weeks. So the plan is, so you know everything now for homework number 2. So that should be fine. Next week we'll be in class again, so you can enjoy the weekend. Don't get too ripped. Where's Tristan? Is Tristan here? How was 21 last Friday? Were you shouting into the big white telephone at the end of the night? Hello! So, in line with the syllabus, not Canvas. So, syllabus has now Isabella's hours on it, as you see here. If you wish to use her, chat with her, as I mentioned before. But we're keeping to our schedule. So we're at the end of week 2. Week 4 are the days of the midterm, Monday and Wednesday and Friday in class, 8 o'clock to 8:30, on paper, hand the paper in, closed notes, closed books. The blue thing is when a review session is up. Of course, I'm very diligent, and the review session is already up. And so you can review that now instead of starting on Thursday. And you'll see that this is well, I actually don't need that, right? So the review session is up here. So this is partway through it. I'll go back to the beginning so you can, I don't know why that's the beginning. So review session goes through everything you need. The midterm is on everything until today, first 2 weeks. It's spelt out here, but I can narrate it exactly for you. It's in the class. I would say come early. Typically, we've done this online and opened it at 7:55 and then gone to 8:31. It's the same as the past questions over the last COVID years. Since 2020, they've been relatively short questions on two sides of a piece of paper. 110 points. You get 110% if you get 110% right. So you get 110% out of 100, which isn't a bad deal. If you bring a calculator, bring a pencil. Don't plan to use your smartphone because it's closed. Not only do you know that we're talking about these things in the first 2 weeks, but you also know what the questions are on Monday and Wednesday and Friday. There are different questions on each of those days. You can look at the video to see what we talk about. You can see that it's all the stuff that we've talked about in class so far. You can look at previous reviews to make sure that I'm not throwing you a line and giving you all the wrong material to study so that you're wrong. I'm not doing that. I don't guarantee that absolutely everything is there, but I think I've absolutely made the most diligent effort to do that. And so ideal gas law, interfacial tension, surface tension, and manometry that we've talked about today. So have a look at that. Yes?
How many questions per day for the
10 short questions with the attempt to not have any lead-ons, right? So that you get one wrong, so you get the next 9 wrong. That's not quite fair. We don't grade on working. We grade on the answer, plus or minus 10% on the answer. This is how we used to do it online. It's just that I'd like to move it into the classroom because I think it's fine. Well, you don't need to know. So just move it into the classroom. See how it goes. So, any other questions? Yes?
I'm just clarifying that I heard this right. Do we have the whole class period, or did you say it only goes till 8:30?
Goes to 8:30.
So would we have learning material the last 20 minutes of class?
No, it lasts. So the reason for that is that some people have extra time on the test. So if I want to get it into the class period, then that takes care of that. So that's the reason. Not a nice thing to have to talk. No, that's fine. So I will tell you again. I don't want to be so patronizing, but this class, the bulk of the assessments are on independent work in the tests. You can study the tests. If I was doing this, fortunately, I don't have to take any tests. I have other demons to deal with. But if I was taking this test, I would go to the previous exams. You have every single solution for every single test for 15 years. They've been like this format, kind of short exams for since COVID, 2020 onwards. And I would pick all of the ones that come within the remit of these topical areas that you see here, Monday, Wednesday, and Friday. I would go to the solutions, I'd look at the tests, I'd look at the questions, and I'd think how I'd solve that and write it down, just what the equation would be that I would use, and see if that's right. And then go to the next one and work through every single one. I think that's the easiest way to do it. But if you're 2 decades into life, you've probably been doing tests of some sort for 1.5 decades, so I won't presume to tell you how to get your stuff together. Great. And on that note, have a fantastic weekend. So.